So in the previous video, we went over some of the underlying theory behind the idea of graphing a derivative. And in this video, we're just going to do some practice problems. So here's problem number one. Problem number one, we have f of x. It's a parabola, right? So also an important note, what would you expect the graph of the derivative to look like? We'd expect it f prime of x to be what? What do we expect f prime of x to look like? Well, we have a parabola, right? And parabolas more often follow the formula y equals x squared plus some other garbage later on. So therefore, and if we take a derivative of anything that has an x squared, we're going to get a linear term, right? Because the x squared eventually simplifies down to something with just an x in it. So therefore, we'd expect f prime of x to be linear, right? So therefore, we're expecting a graph that's just got a line. So we're expecting a line, okay? So that's a key thing to keep in mind. So we're expecting a line as our graph. And the reason this estimation is so powerful is just because it gives us an idea of what to expect. And so this way we know very clearly if we are doing something wrong, right? And we can go back and check some of our intuition. So what's our first step then, now that we've got some intuition? Well, our first step is we want to figure out critical points, right? We want to figure out our critical points. And as a little reminder, critical points are places where f prime of x equals 0. Right? So let's go ahead and find our critical points. And we don't have an actual function to work with here for this graph. So therefore, what we'll need to do is we're just going to have to sort of visually sketch or sketch in our heads what the tangent line would look like at each point along this graph, and then figure out where that would be equal to 0. So it's kind of sloping down, but then over here you actually have a flat tangent just down there. All right, so that's actually going to be where f prime of x equals 0. Okay, and notice that this is at the vertex, right? This is at the vertex of your parabola. And just a key piece of information that will come in handy later down the road, is that vertices or vertices are always critical points. Vertices are always critical points. And this makes sense, right? Because you have something that looks like this, and naturally you should have a vertex down there. You should have a critical point down there. If you have a smooth curve, there has to be some point along this that's for which f prime of x must equal 0, where you have a flat tangent line. But yeah, this is just something that you should really keep in mind, and it's going to be a really powerful idea, because once we're going to use this later on to evaluate local and absolute extrema, right? So just handy bit of information. So now that we have our critical point, we're going to evaluate f prime of x around critical points. Okay, and before we go do that, here's why we actually evaluate the critical points first. Firstly, they're known values, right? You know what the value of the derivative is going to be at that point, so you can clearly set a benchmark, or at least you have some kind of anchors around which you can build your graph. But secondly, it's a key idea to notice that if your derivative ever changes sign or goes from positive to negative, it will do so only around critical points. Okay? So key point, f prime of x will switch signs only at critical points. Okay, another key piece of information there. your critical point is the only place where the graph of f prime of x can switch signs. And think about this, again, you can just think about this intuitively, right? So if a function goes from increasing to decreasing, or positive to negative, it has to touch zero at some point. Or just think about drawing a line on a graph, right? If you're drawing a line that goes from positive to negative, it has to have crossed the x-axis at some point. It has to have crossed through zero at some point, right? So that's an important idea. Now, you don't have to have, the derivative does not have to switch signs every time there's a critical point, but it can only switch signs when there is a critical point. Important thing to keep in mind. So you could have a critical point where the derivative does not switch signs, but at the same time, it will only switch signs at a critical point. Keep that in mind, right? So anyways, that's the second, that's why we actually evaluate critical points. Okay, so now that we've done that, we just evaluate what f prime of x looks like around the critical point. We have only the one critical point, so therefore it makes it, we don't have as much work to do, but let's just take a quick peek at what the sign of the derivative looks at each of these points, across each of these intervals. So we have two intervals, sub-intervals to evaluate, okay? Two places, two main areas where we need to know what the sign of f prime of x will be. So this is interval number 1 and interval number 2. So we need to figure out what the sign of f prime of x will be on these intervals, okay? Over here, take a look at the tangent line. Like, of course, that's a terrible sketch, but you see it's decreasing, right? It's decreasing. The slope of your line is decreasing. It's a little bit like you're rolling a ball down a hill. You're moving down. It's pointed downwards. You start really high and then you're pointed downwards, and now you're sloping towards zero. So over here you're gonna have a negative slope because you have your negative tangent line, right? And you could draw this out more rigorously. So you'd have a negative tangent line here. You'd have a negative tangent line here. You could draw like as many tangent lines as you'd like. All of them would be negative, all right? Let's look at this interval. So over here, you would have a positive tangent line. Over here, you also have a positive tangent line and also a positive tangent line. Now you can draw as many as you'd like, but eventually you will see that you have positive tangent lines all the way around. And so therefore your function is increasing, or you have a positive sign for f prime of x, okay? So now that we have those two pieces of information, we just go ahead and graph. But we need to make sure of one point. You need to exaggerate your sketch. I'm not sure if I spelled exaggerate right, but maybe it's just a 1G, but I forget. Anyways, so you need to make sure you exaggerate your sketch. And what I mean by this is you need to clearly show that you know what the sign are, or you can differentiate between a very negative or a slightly negative, or you need to somehow show to your viewer that you understand what approximately the value of the derivative is at a given point. So let's here's an example. So what's the value of the derivative up here? Well, we don't know, right? But we know that it's going to be a very negative value because you have a very negative slope of the tangent line. Over here, it's not as negative because you're sloping towards zero, and so the graph is and it's not going to be as negative anymore because you're sloping up a little bit. Okay, so you have a less negative slope of the tangent line, or a less negative derivative. What about up here? Well, you have a pretty positive derivative, right? Because it's sloping upwards, and so as you're moving upwards, you're going to have a steeper and steeper tangent line and a lot more and more positive derivative. Okay. Conversely, down here, it's not quite as positive. It's not quite as sloped up, and so therefore you're going to have a slightly less positive derivative. Okay, so that's that. And so therefore, we want to make sure we exaggerate that. We want to make sure we clearly show to the viewer that we understand that. Okay, so we need to keep that in mind. And now let's go ahead and sketch. So we start up here. So the tangent line is negative throughout, right? The tangent line is negative, 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 until we hit 0. Okay, so that's entirely negative until we hit 0. Now and now we hit our second interval where it's entirely positive. And then we go positive, 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 unto infinity. Okay, and that's that's what we have. And does this match our expectation? Well, yes, we expected f prime of x to be linear, so that's matched as well. I know I did a terrible job of sketching it, but it matches our expectation that f prime of x would be linear. So that's our graph of f prime of x. Okay, so those are the main steps that we need to use to solve this problem, and now let's tackle some more complicated ones. Okay, so here's one that you should know. It's not as difficult, but it's something that you really should know. Okay, so here's the slope of, here's an absolute value function, what looks like an absolute value function. Okay, so again, let's take our same steps. We'll take our same steps. So first thing we do is we find our critical points. Now I'm going to add an important point here. This could be two things. I forgot to mention this in the previous example. It could be where f prime of x equals 0, or it could be where f prime of x is undefined. I didn't explicitly state this in the last example, but this is also another definition of a critical point. Okay, so let's go ahead and find those. So what an absolute function is basically two lines. So we have one line this way, one line that way, and so this is the only candidate we have for a critical point. And if you remember, we have actually I'm not sure if I talked about this before, but derivatives are undefined at cusps. Okay, so derivatives are undefined at cusps. And I can we'll eventually learn a more rigorous proof for this, but it's just because when you have a constant slope this way and you have another constant slope this way, both of them are different, and so therefore the derivative here cannot possibly exist, because is it negative 1 or positive 1? You don't know for sure, so therefore you cannot have a derivative at that cusp. Immediately to the right of that cusp, you'd have a slope of positive 1, or whatever that slope is. Immediately to the left, you'd have a slope of negative 1, or whatever that is. Okay, so that's something important, right? So therefore that's our critical value, so we can set our standard there. And second, we'd sketch, or we'd guess or evaluate the value of f prime of x around critical point. Okay, so to do this, let's think about what's going on here. Like I mentioned, this is an absolute value function, which is essentially two lines, right? It's basically two lines converging at a point. Okay, one line goes down like this, one line goes up like that. So therefore, the slope of the tangent line for everything to the left of the critical point, is going to have a constant slope. You're going to have a constant slope. Okay, so because we can, as you can see, the graph actually climbs up one box for every one unit it moves to the right, and so therefore we can say the slope is about +1, or actually the slope would be -1. So we can say that the slope here, or let's see, f prime of x here would be equal to -1. Okay, for everything to the left of 0. To the right, it's the same thing, right? You're climbing 1, you're rising 1 for every run. Every time you run 1, your rise over run is just 1. So therefore, you say that f prime of x equals 1. Okay, quick recap. For everything to the left of our critical point, which is x equals 0, because f prime of x is undefined at cusps, for everything to the left of our critical point, we have a slope of -1. And that's because this is essentially the graph of a line, and lines have constant slopes. So for every value of x left of 0, we will have a slope of -1. Similarly, for everything to the right of 0, we have a slope of 1, because this is also a line. Okay? So, and now, therefore, we can just go ahead and make an exaggerated sketch. Okay? So let's go ahead and do that now. For everything south, or everything to the left of x equals 0, we'd have a slope of -1. And so therefore, until we reach x equals 0, because technically the derivative is undefined at x equals 0, right? So we need to make sure we have a hole over there, because it's undefined at x equals 0, right? And now we do the same thing for everything to the right of x equals 0. Again, f prime of x is undefined at x equals 0, so we'd have another hole over there, but we would still plow on for everything to the right of 0, right? So therefore, we just keep going on like that and that and that. Keep going on forever and ever. And yeah, so that's the idea. All right. So that's how we do that. And absolute value graphs are really important for you to know the derivative, how to graph. It's really important that you understand how to graph the derivative of an absolute value graph, because you'll probably see these a lot. They're very fundamental, and they're honestly not that hard. So it's really important that you understand this. And of course, I have to label my graph. But yeah, that's how you graph this. Okay, and yeah, that's how you do this. Next example. So this one's a little bit trickier because I want to impress on you again what to do if you have multiple critical points and things like that. So let's take a look at this. So we plow through with our same steps. So first thing we do is we find our critical points. Okay. So it doesn't look like f of x is undefined anywhere here. So we're just gonna have to find where f of x equals 0. And so it looks to me that you have 1, 0 over there, because again, remember, it looks like a vertex of a parabola, and those are always going to be 0. It actually looks to me like you have 1 over there, because you see how the graph sort of flattens out, so you'd have kind of a flat tangent line through there. And then you have another one up here, because again, that looks a bit like the vertex of a parabola. So these are the 3 things you have over there. Okay. Now let's evaluate. Okay. We evaluate around our critical points. So if we have 1 through there, 1 over there, 1 over there. It's important we touch the x-axis for wherever we have a critical point, because this is where the derivative is going to cross the x-axis. So it's important that we just clearly mark those points on the x-axis so it's easier for us to sketch later down the road. Okay, so everything to the right of this, let's talk about this interval over here. Everything to the right here is going to have a negative tangent. It's going to have a negative slope, right? Because again, you should be pretty good at this by now. You should see that the graph is decreasing or is going to have negative tangent lines all the way through until here. So therefore, we can say that everything to the left is going to have a negative sign for f prime of x. Okay. Now, what about between here and here? Well, that's going to be positive, right? Because again, we're slowly increasing. It's eventually leveling off, but we're still increasing. Now what about between here and here? Again, you should see it's still increasing. It's still increasing. It hit where it went to 0 there, but it's still increasing. And then this is also a clear indicator, or it's an example of the fact that a critical point is not necessarily always a place where it's a reminder that your f prime of x does not always switch signs at critical points. It can only switch signs at critical points, but it doesn't always do that. Okay, so it's going to be positive both sides of this critical point. Now, what about here? From here until like eternity, it's going to be negative, right? Because as you can see, it's decreasing and it has no indication of stopping, so it's going to be negative throughout. Okay. So given this information, we can now make our exaggerated sketch. And again, it's important that we exaggerate exactly how negative or how positive. We exaggerate our sketch to make sure we indicate how positive or how negative the slope is. Okay, so now let's sketch this thing. So we're going to start very negative, okay, and then we're going to climb up. I'm going to climb up until we reach this. Okay, and then we're positive, right? So we're going to go above the x-axis just for a little while, but then we're going to have to dip back down to 0 because we have a critical point over there, and then we go back up again, but then we're going to have to dip back down because we have another critical point over there, and then eventually we just keep going more and more negative. Okay, so that's kind of what it would look like. It's not a very good sketch, obviously, because I haven't been very clean with my curves and stuff here, but that's what this would look like. All right, so that's this example, and you can't actually compare this to anything, but at the same time you kind of get an idea of what this would look like. All right, so that's what we'd have here. Last example. This is just a it looks a bit like a kind of x cubed function. So here's what we're going to do. We're just going to go ahead and just carry out our regular steps. So firstly, we're going to have to evaluate our critical points. Again, it doesn't look like f prime of x is going to be undefined anywhere. So we're just going to find our critical points, and we're going to have one over there. We'd have one if it was down here, but we're just we can omit that. Then we're gonna have another one maybe around over there, so maybe just around there, and it keeps going up from there, so we don't really need to worry about that. All right, so now let's evaluate. Around critical points. Well, to the left of this critical point, we're going to be mostly positive, right? We're going to be positive all throughout because we're increasing throughout, right? We're increasing. We're not increasing at a constant rate, but we're increasing throughout, so we're going to be positive. Now, what about this side? Well, we're increasing throughout, so it's going to be positive. And beyond this, we're still increasing, so it's also going to be positive, right? So important to note. So we're basically we're positive throughout, but not at a constant rate, which is why we have we touch the x-axis at many points. All right, so that's the idea. Now let's make an exaggerated sketch. Well, over here, it's actually kind of flat to begin with, so we're actually going to start very close to 0. And then, so we're actually going to start very close to 0. We're going to go higher because we have that kind of a steeper slope over there. But then eventually we're going to come back down just because we're leveling off over here. So we're going to come back down, but then we're going to go up again because we're still increasing. So we're going to keep going up. We're going to keep we're going to keep increasing. It's going to get very positive, but then we're going to start to level off again, because we've got that critical point there, and as you can see, where it starts to level off as we approach it, but then we keep going up again, and we go up until eternity. At least as far as we're concerned with this graph, we're just gonna keep going up for now. It may have another critical point later down the road, but we don't care. And as you can see, I didn't do a very good job of sketching this curve, because I've put a little bit of it below the x-axis and stuff like that, but that shouldn't happen. Ideally, this entire curve should be above the x-axis. Right? So important to make sure you're not sloppy that way, and make sure your curves are also very distinct, because if you're sloppy, sometimes your curve can look a bit like a cusp, which you don't want. People will penalize you for that. So you want to make sure your curves are smooth and everything is very, very clear to whoever's viewing. All right. So anyways, that's it for this video. I hope you found it helpful. I hope you really got the ideas behind it. If you found this video helpful, please do like, share, subscribe, leave a comment, and check out some other videos. See you next time.